This video is about teaching machines to reason with reinforcement learning. Modern large language models can solve math problems, write complex code, and tackle logic puzzles.
The riddle reads as: a princess is as old as the prince will be when the princess is twice as old as the prince was when the princess's age was half the sum of their present age. It's not the easiest problem, but we got the answer just right.
It's remarkable. However, reading papers on this topic can be overwhelming, but it's actually incredibly satisfying to learn how intuitive ideas have stacked together to unlock the reasoning capabilities of LLM. In this video, we will start from the basics and progressively build up the advances over the years that led to an effective learning algorithm. Given a question, our language model first predicts the probability distributions over all possible tokens. Sample from this distribution gives us a specific token. Then we move on to predicting the next token, one step at a time. This is what we call autoregressive generation. At the end of the process, a reward model steps in to check the answer's correctness. If the answer is right, it scores a 1, if not, a 0. For math, we verify the correctness by matching answers. For coding, we run the generated code to see if it passed the unit tests. Let's break this down with some notations. The question itself is our starting state as 0. This is a state S at time 0. We think of the language model as a policy. It's a function that takes the current state as input and returns a probability distributions over all possible actions. In our case, tokens in our dictionaries. Sampling from this distribution gives us a specific action, U0, the first token. We then form a new state S1 by concatenating the questions with this generated token. Our policy then uses the state S1 to predict the probability of the second token. The process repeats until the end of sequence EOS token is generated. We call the full sequence of states and actions a pass, denoted by tau. At each time step, the environment can give us a scalar reward indicating how well the model is doing. The total reward of a pass tau is the sum of the reward from state action pairs over time. For reasoning tasks, this reward usually comes only at the very end. In contrast, in other tasks like learning to play Atari games, you might receive rewards at every time step. Basically, we are training our LLM to reason like we train this chicken. Our goal is simple: find the parameters of our policy that maximize the expected total reward. In other words, we want to boost the weighted average rewards from all possible paths. But how do we achieve that? Imagine our policy has only one parameter theta. Picture a 1D curve representing the utility function, our expected reward. Starting from a random point, we compute the gradient of this utility function with respect to our parameter theta. The gradient tells us exactly how to nudge the theta to climb toward a higher reward. Now let's see a 2D case. We start with the initial parameter theta and move along the gradient directions that give us the fastest increase in utility. Here is the gradient is a 2D vector made out of partial derivatives, capturing the rate of change along the first dimension and the second dimension. We denote this using a gradient operator. Of course, in a large language model, we are dealing with billions of parameters, but the principle remains the same. So how do we compute this policy gradient? We start by moving the gradient operator inside the sum over all trajectories. But here's a challenge: summing over every possible path is computationally infeasible. Let's add a dummy term and rearrange our expression. We can apply a chip here to simplify this term to the gradient of the log probability. Why is that? Think of it this way: when differentiating a composite function, you multiply two derivatives. The derivative of z with respect to x is the multiplication of the two derivatives. This is known as chain rule. Now let's look at the expression of the log probability. The gradient of the log probability is the multiplication of the two gradients. This is what we call the log derivative trick. By expressing the gradient of the expected reward in this form, we can recast it as an expectation over the distribution of paths. Computing this expectation analytically is too hard, but we can approximate it with multi-color estimation by using sample trajectories generated by the policy. The intuition is simple. The gradient pushes up the probability of paths that earn positive rewards, while pulling down the ones that yield negative rewards. We can teach our model to reason through this iterative refinement. But our policy takes the state as input and predicts the probability over possible actions. Let's break this down further by decomposing a path into a sequence of state-action pairs. Recall that a path tau is simply a sequence of states and actions. The probability of observing a particular path tau is given by the product of two terms. The dynamic model, this represents the probability of transitioning to the next states, given the current states and the chosen actions. The policy's probability, this is the probability of taking a specific actions given the current state. When we apply the logarithm to this product, the multiplication turns into a sum. And here's the key insight. Since the state transition dynamics do not depend on our policy's parameter theta, this term associated with the dynamic model disappears when we take the gradient with respect to theta. We can then plug this simplified expression back into our gradient estimate. The intuition remains consistent. The gradients are essentially nudging the policy to increase the probability of generating the next tokens for paths that result in positive rewards, and decrease it for those that yield negative rewards. But this is quite noisy. For example, consider that the total reward along a path is the sum of rewards received at each time step. The action at time t should not be credited for the rewards that were earned before the action occurred. So what do? We adjust our gradient estimations by removing these earlier rewards. This way, the gradient update depends only on the reward accumulated from that specific time step onward. This ensures that each action is only credited or blamed for the rewards it directly influences. But here is a challenge. In many problems, the rewards are all positive numbers. This means that every action along every possible path gets a positive reward. However, our policy must predict probabilities that sum up to 1. As a result, training can take a long time to converge. So, how do we speed things up? We introduce a baseline. This baseline estimates the expected total reward from the current state onward under the existing policy. We call this baseline a value function. If the observed reward for an action is higher than the expected cumulative reward, the baseline, we boost the log probability of that action. Conversely, if it's lower, we decrease it. This way, each action is adjusted only relative to its performance compared to the average performance, making learning more efficient. But very often, the possible states are just too large. For example, when states represent all possible texts, we simply cannot use a lookup table. Instead, we approximate the value function with a neural network. This network serves as a function approximator that estimates the expected return from each state. We train this network by minimizing the difference between its predicted expected return and the actual observed one. This is great. Now we learn the value function to approximate how well the policy performs at each state. But here's the catch. This guy here is estimated from just a single sample that estimates the expected total reward if we take action U at state S. Because it's based on only one sample, it has low bias but high variance. What does that mean? Imagine throwing a dot at a target. A low bias estimate suggests that on average, your throw hit near the center of the target. But high variance means that from one throw to the next, your results can vary widely, even if the average is spot on. You can also have an estimate that's consistent yet low in accuracy. That's low variance but high bias. In our case, the target is the true expected reward when taking action U at state S. Estimating this expectation from a single sample gives us a low bias and high variance estimate. So how do we reduce this variance? First, instead of summing up the total reward, we introduce a discount factor, gamma, between 0 and 1. The intuition is simple. An action at time t is likely to have a stronger impact on the near future than on the distant future. By discounting future rewards, we account for this decay in inference over time. Let's simplify things by calling this adjusted estimate the advantage function. When we estimate the advantage function from a single pass, we are using Monte Carlo estimation. It's accurate but can be inconsistent, low bias but high variance. Alternatively, we can group the discounted future reward starting at t plus 1 and approximate them using our learn value function at state t plus 1. This approach is known as temporal difference estimation. Temporal difference has low variance since it relies on our learn value function, but it can be biased because the value function may not be accurate. To balance the bias-variance trade-off, we can look ahead multiple steps. This idea is used in methods like A3C. But why choose a specific number of look-ahead steps? Generalized Advantage Estimation, GAE, provides an elegant solution. GAE computes an exponentially weighted average of all the estimates, from pure Monte Carlo estimation to temporal difference, using a parameter lambda. This parameter lambda smoothly interpolates between high variance, low bias, and low variance, high bias estimates, giving us a robust advantage estimation. Let's recap what we covered so far. Here is our gradient estimate for updating the policy. We start by initializing our policy network from a pre-trained language model, often one that's already been instruction or preference tuned. Next, we run the language model on a set of questions, collecting its response and the reward associated with them. For every state action pair along the way, we estimate the advantage function. Then, using gradient-based optimization, we update both the value function and the policy network. This combined process is known as the Actor-critic method. The actor refers to our policy network that takes action given the state. In our context, it's a language model that predicts the probability of the next token based on the prompt and all previously generated tokens. The critic refers to the value function that estimates how good the state is, essentially providing feedbacks to the actor on whether its action led to the outcome better than expected. This is great, but there are two fundamental problems. First, even though we have a gradient estimate for updating our policy, choosing the right step size or learning rate is tricky. If the step size is too small, then the training becomes too slow. If the step size is too large, then you risk disastrous policy update, which in turn leads to collecting bad data, and we cannot recover. After we generate 4 responses from our policy, we only get a single gradient update. This is because the gradient estimate depends on the current policy parameter, theta. This is what we call on-policy learning. Imagine you are learning to play tennis. On-policy learning is like practicing your swing and fine-tuning your posture in real time. Now imagine you could record your training session and review it multiple times afterward. That way you'll reuse your past experience from your older self to improve your skills faster. That's great, but our current method limits us to 1 update per experience. Let's see what we can do. First, let's simplify by focusing on time t only. We can rewrite our sample average as a sum over a term weighted by the joint probability of state and action. We can only update the policy once because these states and actions are generated by the current policy. Fortunately, we can apply a trick called importance sampling to break this dependency. Here is a simple example. Imagine we want to estimate the expectation of a function f of x, where the sample x are drawn from a probability p of x. Suppose the function f of x is just a straight line, and the probability density p of x follows this blue curve. If you compute an expectation using Monte Carlo estimate, you may expect a negative value. It's pretty reasonable. But what if we want to estimate this expectation using samples drawn from a different probability distributions, q of x? You can still do that by assigning each sample an importance weight equals p of x divided by q of x. Even if you have fewer samples in regions where q of x is low, these samples carries a larger weight because p of x is higher there. The Monte Carlo estimates with importance sampling also gives you an accurate result. So why does this work? We multiply by a dummy term and swap the position of p and q. This lets us rewrite the expectation in terms of samples from Q instead of P. Now back to our gradient estimate for our policy. By introducing a dummy term and swapping distributions, we can reframe this expectation in terms of samples from an old policy. We factorize the joint state action probability into the probability of the state and the policy. And assuming the state distribution doesn't change much, we arrive at a neat expression for our gradient estimate at time t. With this gradient in hand, we can derive the objective function as this. But wait a minute, why is that the case? Let's verify. Take the gradient with respect to the parameter theta, move the gradient operator inside, since only this term depends on theta. Multiply by a dummy term, and rewrite it using the log derivative trick. Yes, it all checks out. This is known as the surrogate objective. Now we can run gradient-based optimization to train our policy networks for multiple epochs, using data collected from an older version of our policy. It's like watching the recordings of your tennis game multiple times to fully distill the lessons you learn from the experience. But there's a catch. This won't work if the current policy, theta, and the old policy, theta O, differ too much. First, the estimate from important sampling will have high variance. Second, the advantage function estimated under the old policy may be inaccurate. To prevent the policy from drifting too far away, we add a constraint between the current and the old policies. This technique is called Trust Region Policy Optimization, or TRPO. TRPO ensures that each update stays within a trust region, so that our updates remain stable. But making this constraint optimization work is tricky. It involves a second-order optimization problem, along with various approximations to make it tractable. Let's try simplifying this. One simple approach is to transform the hard constraint into a penalty term. Now our problem becomes unconstrained, and we can apply standard gradient-based methods. This is a version of proximal policy optimization, often referred to a PPO penalty. The main challenge with PPO is choosing the right weight for the KL penalty, denoted as beta. PPO proposes an adaptive method. If the KL loss is larger than the threshold, it indicates that the penalty is too weak, so we increase the beta. Conversely, if the KL loss is below a threshold, the penalty is too strong, so we decrease the beta. This is nice, but can we simplify this even further? Let's examine the core objective function. We denote the probability ratio as R theta. Now consider two scenarios. If the advantage is positive, it means that the action is better than expected. In that case, we want to increase its probability of taking that action to maximize our objective. If the advantage is negative, it means that the action is worse than expected, so we want to decrease its probability of taking that action. However, this objective is valid only when the current policy is close to the old policy, when the probability ratio stays near 1. To enforce this, we clip the ratio between 1 minus epsilon and 1 plus epsilon. For example, when the epsilon is 0.2, the ratio R theta is clipped between 0.8 and 1.2. For a positive advantage, the optimization encourages increasing the probability, but once the ratio exceeds 1.2, the objective flattens out, stopping further increases. For a negative advantage, a similar effect occurs. If the ratio drops below 0.8, the objective starts further decreases. But here's the problem. If the current probability ratio is within this region, the clip objective actually do not increase the probability when the advantage is positive, or decrease the probability when the advantage is negative. To fix this, we combine the original objective with the clip one by taking the minimum of the two. This yields the yellow curve. With this, the probability ratio is nudged in the right direction, increasing for actions better than expected and decreasing for those worse than expected, all while preventing excessive deviation from 1 through clipping. This refined objective is known as PPO clip. It's simpler than the adaptive KL penalty variant and often performs better. When we talk about the PPO algorithm, we usually refer to this particular variant. Let's go back to the state action view along the path. Here's a simple illustration of how we compute an advantage function. We start with the question as the state S0. Then, using the policy model from the previous iteration, we generate a response denoted by tau. Next, a reward model evaluates this response and assigns rewards based on its correctness and format. At the same time, a value function predicts the expected reward from each time step. By combining the observed rewards with the value estimate, we compute the advantage at each time step using Generalized Advantage Estimation. But besides training the policy network, we also need to train this value function network concurrently. This effectively doubles our memory and computational requirements. How can we simplify this? Instead of generating just one output per question, we can generate a group of outputs. We then run our reward model on each output and assign rewards accordingly. Next, we normalize these rewards within the group, subtracting the mean and dividing by the standard deviation to obtain the advantage for each pass. In this approach, every time step along a given path uses the same advantage value. This simple and efficient algorithm is called Group Relative Policy Optimization, or GRPO. It's the core learning algorithm behind the success of DeepSeek-R1. But there's more. Training solely with this objective might cause our policy to drift too far from our reference model, for example, the initial preference-tuned model. To prevent this, we add a KL divergence penalty between our current policy and the reference model. This regularizes the training by ensuring that the next token probabilities stay similar to the reference models. Directing computing KL divergence is expensive, but we can approximate it with a low bias estimate. But two challenges remain. First, there's a lens bias in the training objective. When the advantage is positive, meaning the answer is correct, the objective tends to favor shorter responses because the term is divided by the response length. When the advantage is negative, that is, the answer is incorrect, the objectives encourage longer answers. In other words, the training might push the model to produce unnaturally short responses for correct answers, while encourage the model to favor artificially longer answers when the answer is incorrect. Second, the difficulty bias. For questions that are very simple or very difficult, the variability of rewards tends to be small, leading to larger advantage values. On the other hand, questions of medium difficulty, where some outputs succeed and some fail, yield a larger standard deviation and therefore smaller advantage values. This imbalance can skew the learning process by overemphasizing extreme cases. To counter these issues, we remove the normalization by path length to address the lens bias. We eliminate the division by the standard deviation to tackle the difficulty bias. This refined variant is called Dr. GRPO. It delivers similar performance levels without artificially inflating the chain of thought reasoning paths. I hope you enjoyed this overview. Thanks for watching, and I'll see you next time.